Welcome back to the Deep Dive, your essential shortcut to understanding the most fascinating breakthroughs in AI and machine learning research. And remember, for links to the papers and other resources we discuss, just check out the bio on our webpage. Today, we're plunging into a topic that really gets to the very heart of how large language models, or LLMs, are learning to think.
Mm-hmm.
And maybe even more remarkably, how they're learning to improve their own thought processes.
Yeah, it's pretty cutting-edge stuff.
Now, if you've been following the AI space, you've probably been absolutely astounded, just like we have, by the incredible reasoning abilities LLMs have shown in very structured tasks.
Oh, definitely.
We're talking about things like solving complex math problems that stump most humans,
Mhm.
or generating flawless code that passes unit tests with flying colors. It's truly impressive.
The progress there has been phenomenal, really.
But here's the fundamental challenge, right? Extending these truly impressive, almost magical reasoning capabilities to more open-ended, long-form, and nuanced tasks. Well, that's been a persistent, significant hurdle.
Absolutely. It's a whole different ballgame.
How do you objectively tell if an LLM is truly reasoning well, if it's genuinely improving its thinking, when there isn't a single definitive right answer to check against?
Exactly.
Think about it. How do you grade the quality of, say, a beautifully revised document or a comprehensive financial report or even a creative story? It's subjective, isn't it?
It really is. There's no easy metric.
Well, that's precisely what we're here to deep dive into today. We're going to unpack a groundbreaking paper that recently emerged from Microsoft and UCLA.
Mm-hmm.
This paper introduces something truly novel called direct reasoning optimization, or DRO,
ARO, yeah.
and a brand new reward signal that it uses, which they brilliantly named the Reasoning Reflection Reward, or R3.
R3. Catchy name.
Our mission in this deep dive is to pull back the curtain and show you how these innovations aren't just like incremental steps. They represent a fundamental shift in how LLMs can essentially reward and refine their own reasoning.
That's the key, the own reasoning part.
Exactly. We'll focus particularly on those complex, open-ended problems where traditional human feedback is subjective, inconsistent, or just too expensive and slow to provide at scale.
Which is a huge bottleneck in practice.
So get ready to explore the technical brilliance that could very well define the next wave of self-supervised LLM fine-tuning. We're giving you a shortcut to understanding the cutting edge of what's possible here. So let's unpack this core idea first. As we just mentioned, LLMs have blown us away with their abilities in highly structured tasks, like math problems and programming challenges. Why is that?
Yeah, that's the foundation.
The paper points directly to a concept called reinforcement learning with verifiable rewards, or RLVR. What's the secret sauce that makes RLVR so effective in these specific domains?
Okay, yeah, that's absolutely the right place to start. Because understanding RLVR really sets the stage for appreciating the problem R3 is trying to solve.
Right.
The huge success of LLMs in these structured tasks, solving equations, debugging code, even acing multiple choice tests, it's largely down to RLVR. The secret sauce, as you put it, lies in using incredibly objective, clear-cut, unambiguous signals of success.
Verifiable rewards.
Exactly. Verifiable rewards. Imagine a math problem. The reward can be as simple as checking if the final answer matches a reference solution, maybe within a small tolerance.
Okay, straightforward.
For coding, it's even more precise.
Mm-hmm.
Did the generated code pass all the predefined unit tests? Did it compile?
Right or wrong?
Right or wrong? Binary. Concrete. That clarity is what makes them so powerful.
And scalable, I guess.
Absolutely scalable and robust. You can compute them automatically, no humans needed, millions, billions of examples, instant feedback.
Wow.
And critically, they are remarkably robust against reward hacking,
Yeah.
where the model learns to game the system.
Yeah, finds a loophole to get the reward without actually solving the problem.
Precisely. With verifiable rewards, it's incredibly hard to cheat. The criteria are just too concrete. It either got the number right or it didn't. The code ran or it didn't. No ambiguity.
That makes perfect sense. Clear answer, clear reward.
Mm.
But okay, here's where it gets really interesting and frankly quite challenging.
Mm-hmm.
If RLVR works so brilliantly for math and code, why is applying that same powerful principle to truly open-ended tasks like, say, revising a nuanced legal document, composing a comprehensive market report, or even just crafting elegant prose? Why is that so incredibly difficult?
Yeah.
You'd think the underlying principle of rewarding good output would still apply, wouldn't you?
You'd intuitively think so, right? But the core difficulty, as you've highlighted, is exactly the absence of those generic, universally verifiable reward signals for these open-ended tasks.
Mm.
When you revise a document, there isn't one single correct revised paragraph. Often there are multiple good ways to phrase something, several valid ways to adjust feedback, different structures, all perfectly high quality.
So inherent subjectivity.
Exactly. Subjectivity and multiplicity of correct answers. That makes it incredibly hard, maybe impossible, to define an objective automated reward like you can for a math problem.
And this isn't just theoretical.
Oh no, not at all. It directly exposes the limits of existing approaches for complex, real-world LLM tasks. Take traditional similarity metrics, for example.
Like Rouge scores or cosine similarity.
Precisely. Things like Rouget, cosine similarity, they measure textual overlap or embedding similarity, but they just fall short for these open-ended tasks.
Why is that?
Because they mainly focus on lexical similarity, how many words overlap, how close the meaning is at the word level. They don't capture the deeper logical coherence, the reasoning consistency, or if the task's intent was actually met.
So they miss the forest for the trees.
Exactly. Imagine that paper revision task again. A revised paragraph genuinely improves the flow, clarifies the argument, maybe rephrases sentences significantly.
A good revision.
A great revision. But a ruse score might give it a low mark because it doesn't overlap much textually with the original or maybe even the reference if the human also made big changes.
Ah, I see.
Conversely, a model could just copy chunks from the original superficial stuff, get a high Rouge score for overlap, but completely fail at the actual reasoning or improvement.
So it masks the reasoning ability.
Totally masks it. It's like evaluating a chef based on using the same brand of salt, not how the dish tastes.
Okay, so similarity metrics are out. What about external dense reward models?
Right, the next approach. These are usually separate, often very large LLMs trained specifically to give detailed feedback on another LLM's output, trying to mimic human preference.
Sounds plausible. What's the catch?
Several catches, actually. First, they need vast, high-quality, preference-style datasets. Think humans meticulously comparing millions of outputs, labeling which is better.
That sounds expensive.
Hugely expensive.
Dude.
And time-consuming. For many specialized open-ended tasks, summarizing niche scientific papers, deep financial analysis, these datasets just don't exist. Creating them is often prohibitive. It's a massive bottleneck.
Okay, data scarcity. What else?
Second, training and running these external reward models adds significant computational overhead. You're essentially running two big models, the generator and the judge. More complexity, more cost.
Right.
And maybe worst of all, they're highly susceptible to reward hacking themselves. The model being optimized can learn to trick the reward model into giving a high score without actually getting better at the task.
Like gaming the grader instead of learning the material.
Exactly. The feedback loop gets corrupted.
Okay, so external models have issues too. What about the last one? LLM as a judge. Using one LLM to evaluate another. Seems intuitive.
It does seem intuitive on the surface, but the paper points out several critical problems here too. They are incredibly sensitive to prompt design and the evaluation rubrics you give them.
How sensitive?
Very sensitive. A tiny tweak in the instructions, even a single word change in the prompt for the judge, can drastically alter its assessment. Makes the judgments inconsistent and hard to trust reliably at scale.
Consistency issues.
And there's often a self-enhancement bias. LLMs might subtly favor outputs similar to what they themselves would produce, a sort of algorithmic narcissism.
Okay.
Plus, there's the generator-discriminator gap. A model great at generating creative text isn't necessarily a robust, unbiased judge, especially for subtle quality differences.
Right. Different skills.
And most importantly for today's discussion, extracting a dense, task-specific reward signal from an LLM judge is really challenging. It's not, as the paper says, turnkey or reliable.
So it needs a lot of tailoring for each use case.
Exactly. Careful, labor-intensive tailoring, validation, constant maintenance for each specific task. That undermines the goal of automating and scaling the fine-tuning. And trying to evaluate the nuances of chain-of-thought reasoning with an external judge is even harder because the judge doesn't see the internal process.
So, okay, we've seen why the usual tricks, similarity metrics, external reward models, LLM judges won't cut it for these complex, open-ended tasks. They're shallow, costly, hackable, or unreliable. It feels like we're stuck.
It certainly highlights the limitations.
What's the novel approach this paper proposes to get out of this bind? This is where direct reasoning optimization, DRO and the reasoning reflection reward, R3, finally step in?
You've perfectly framed the problem, and yes, this is precisely where DRO and R3 flip the script entirely. To overcome these limitations, the paper introduces direct reasoning optimization, DRO.
Okay, DRO.
Think of it as a sophisticated reinforcement learning framework, specifically engineered for fine-tuning LLMs on these challenging, subjective, open-ended tasks.
And the core innovation.
The core innovation, the real game changer here, isn't just tweaking an old reward signal. It's a brand new, internally derived one they developed. The reasoning reflection reward, or R3.
A reasoning reflection reward that really grabs your attention? What's the big picture here? How does it fundamentally differ from everything we've just discussed, especially in how it rewards reasoning?
The big picture with R3 is really elegant and potentially quite profound. Its core mechanism is to selectively identify and emphasize key tokens in the reference outcome that directly reflect the influence of the model's preceding chain of thought reasoning.
Okay, key tokens reflecting reasoning.
Exactly. This is crucial because it allows the system to capture the consistency between the reasoning process itself and the desired outcome at a really fine-grained token level.
But how does it find those tokens? And how does it avoid the problems of external judges?
Here's the truly crucial technical aspect, the paradigm shift. R3 is computed internally using the same model being optimized.
Wait, the model rewards itself?
Essentially, yes, let that sink in. The model generates reasoning, generates the outcome, and then without any external help, it evaluates its own reasoning's consistency with a given reference output.
Wow, so no external reward model, no human annotators needed for the reward signal.
Precisely. It eliminates reliance on external models, annotators, or separate verifiers. This enables what they call a fully self-contained training setup.
What are the benefits of that?
Huge benefits. Dramatically reduces computational overhead, cuts annotation costs for the reward signal itself down to basically zero, and significantly lowers the risk of external reward model hacking.
It's like the LLM becomes its own internal critic.
A self-aware learner, exactly. A highly discerning internal critic. That's the potential here.
This idea is self-contained training, where the LLM rewards itself based on its own internal reflections. It's just fascinating. It's like it develops an internal compass. Can you break down the technical magic behind R3? How exactly does the model reflect on its own reasoning and assign these internal rewards?
Okay, let's pull back that curtain. It starts with a fundamental property of LLMs, their autoregressive nature. They generate one token at a time, predicting the next based on everything before it.
Right.
In this context, the chain of thought, the COTI reasoning the model generates before the final answer, acts as what the paper calls a latent prefix.
A prefix?
Yeah, a conditioning prefix. It sets the stage, it influences the generation of the final outcome that follows.
Okay.
So the model's token-level certainty, its log probability for generating each specific token in the reference outcome, when measured under the influence of this reasoning prefix, directly indicates how likely that reasoning path is to produce the correct outcome.
So high certainty means good reasoning.
Intuitively, yes. Think of log probability as the model's internal confidence. High score means high confidence. Low score means it's surprised, almost guessing. If the reasoning is sound and aligns logically with the expected output, the model should be highly confident generating the reference outcome tokens.
That confidence, that internal certainty, is the raw material R3 uses.
Exactly. That's what R3 taps into.
That makes perfect intuitive sense. Strong reasoning leads to high confidence about the right answer. But the paper points out two key blind spots or issues with just naively using this internal confidence. It's not as simple as just summing up all the log probabilities, is it?
No, exactly. The intuition is strong, but reality is subtle. The first blind spot is key reasoning token blindness in log probability aggregation.
Token blindness.
Yeah. The issue is, in a long output, like a revised paragraph, most tokens get very similar log probability values, regardless of the COTI reasoning that came before.
Why is that?
Think about common words. The A is standard phrases. The model is always super confident about predicting those, almost on autopilot. These high-confidence, low-information tokens dilute the signal from the important bits.
So only some tokens actually reflect the reasoning?
Precisely. Only a limited subset truly reflect reasoning variations. These are the reasoning reflective tokens. Let's use the pararev task example from the paper's Figure 1, paper revision task.
Okay.
Imagine two COTI reasonings. Reasoning A correctly identifies that Section 4 needs reordering before Sections 2 and 3 is structural change. Reasoning B just gives up on logic and makes superficial text changes.
Right.
Now, a naive aggregation of certainty across all output tokens might actually prefer reasoning B over A.
Wait, why? Reasoning A is better.
Because reasoning A, while logically superior, might have slightly lower certainty on a single critical token, maybe the numeral 2, if it's moved to an unexpected place like section 2 moved here.
A single low probability token.
Exactly. That single token, though crucial for signaling the successful reasoning, the reordering, gets diluted. Its influence is masked by the volume of other high-certainty, less informative tokens. The problem is these critical reasoning reflective tokens often have lower log probs precisely because they signal specific, complex reasoning outcomes. Their influence gets lost in the noise of the long sequence.
Okay, that's the first blind spot. What's the second one?
The second is equally subtle but important. When reference tokens compensate for poor reasoning, this is more insidious.
Compensate. How?
When we compute the model's certainty for a token, we condition not just on the Ka-T reasoning, but also on all preceding reference tokens from the ground truth. This is standard autoregressive behavior.
Teacher forcing.
Kind of like teacher forcing, yes, but it can artificially inflate the overall reward signal, making the reasoning look better than it was.
Can you give an example?
Sure. The paper's Lionel Messi example is perfect. Suppose the Ka-T reasoning is flawed, leading to low probability for Lionel. But then Lionel is given as part of the reference sequence.
Okay, you force the first name.
Right. What happens next? The token Messi is almost certain to get a very high probability Y. Massive lexical association between Lionel and Messi.
Of course.
So even though the original reasoning might have been poor, giving the model the correct previous token Lionel effectively compensates for that error. It leads the model to overestimate the Ka-T quality.
Like giving a student the first step of a math problem, making the rest easy.
Exactly. And this compensation effect gets worse in longer sequences with strong co-occurrence patterns. It makes it really hard to attribute success purely to the reasoning.
Okay, so R3 recognizes these two critical problems: blindness to key tokens and compensation from reference tokens hiding bad reasoning. That's where the reflection part really comes in, I guess. How does R3 tackle these two tricky blind spots?
That's right. R3 is engineered to be much more discerning. To address the key reasoning token blindness, it doesn't treat all tokens equally. Instead of complex semantic analysis, which doesn't scale,
Right.
it uses a brilliant comparative approach. It identifies reasoning reflective tokens as those whose likelihoods show high variation when conditioned on different Ka-T traces for the same problem.
So if a token's probability jumps around depending on the reasoning path.
It's likely important for evaluating that reasoning. Exactly. Looking back at that figure 1 example, maybe tokens like gives existing or even a period show high standard deviation in their log probs across different tokens. Those are the subtle signals reflecting the reasoning's impact.
So how does R3 use this variation?
Technically, it weights each reference token's log probability contribution according to its standard deviation across different Ka-T traces. Tokens with higher SUs, more sensitive to the reasoning path, get greater weight in the reward calculation.
Amplifying the important signals.
Precisely. It's like the model learns to listen to its own intuition about which parts of its thought process really mattered. An internal spotlight on the critical reasoning moments, preventing dilution. It focuses the reward on reasoning quality, not just surface text.
Clever. And how does it address this second challenge, the compensation for poor reasoning?
Right, the compensation effect. R3's insight is, poor Ka-T leads to low confidence initially. But once the reference sequence corrects a token, it creates that artificial error compensation chain.
Masking the problem.
Exactly. R3 offers two solutions. First, a targeted decay mechanism. Think of it like a ripple effect, starting specifically at those crucial reasoning reflective tokens.
A ripple?
Yeah, the model's confidence propagates forward from those key points, but it's controlled. The influence fades out over a localized window of subsequent tokens. There's a propagation factor, P prop J, considering the reflective token's certainty and distance with the decay hyperparameter, gamma.
So the reward stays focused near the key reasoning point.
Exactly. It prevents the reward from being inflated far down the line just because the reference helped early on. Useful for long sequences.
That sounds a bit complex, though.
It is computationally intensive, so they also propose a more efficient alternative, which is really quite ingenious.
Okay.
This alternative computes the reference token log probabilities, but conditioned on a masked Ka-T.
Masked Ka-T, meaning No reasoning influence.
Exactly. They effectively remove the influence of the generated reasoning. This mascot log probability becomes a baseline, the certainty coming only from the reference tokens themselves.
I see. And then?
Then, by subtracting these masked cot log probabilities from the ones computed with the model's actual cot t, R3 isolates the certainty boost coming directly from the reasoning.
Ah, so it cancels out the compensation effect.
Precisely. It elegantly removes the compensation from the reference tokens, ensuring the reward truly reflects the cot quality, not just the model's knack for predicting common word sequences based on the reference. It normalizes the self-certainty.
So R3 is this brilliant internal reward signal, pinpointing and rewarding effective reasoning. But DRO was presented as a complete fine-tuning framework, not just the reward.
Correct.
How does it fit into the broader RL landscape, and what other components make the whole system powerful?
You're spot on. R3 is the heart, but DRO is the full system making it beat effectively. It's an RL fine-tuning framework strategically applying this reward. DRO builds upon a solid foundation, Group Relative Policy Optimization, or GRPO.
GRPO, a variant of PPO?
Exactly, a powerful variant of proximal policy optimization. Quick GRPO refresher. For a given prompt, the model generates not just one cot trace and outcome, but a group of them, say 16 or 32 different reasoning paths and answers.
Okay, a batch of attempts.
Right. Each trace is scored using R3. Then GRPO computes an advantage estimate for each trace, but relative to the mean and standard deviation of rewards within that same group.
Relative advantage. Why is that important?
It's key because it encourages the model to assign higher probabilities to trajectories that outperform their peers in the same batch. It constantly pushes the model to generate better reasoning by comparing its own attempts, not chasing an absolute score, a very effective competitive dynamic for refinement.
Makes sense. Are there other reward components in DRO besides R3?
Yes, a practical nuance. While R3 rewards the reasoning trace, they found that only rewarding reasoning could sometimes make models too verbose in the final output.
Rambling.
Potentially. So DRO cleverly applies a length penalty solely on the final outcome, not the reasoning chain.
Concise answers but elaborate reasoning allowed.
Exactly. The final reward is a weighted combination. R3 score plus this outcome length penalty ensures intelligent reasoning and practical output. Very thoughtful design.
And you mentioned the internal policy for R3, RED.
Right, the policy used for computing R3. It can be static, original reference policy, dynamically synced with the main actor policy being optimized, or a lagged version updating slightly slower. This flexibility lets researchers tune how the model judges its own work during training. Another knob for optimization.
Okay, that framework sounds robust. The paper also mentions dynamic data filtering. Why is that important, especially for open-ended tasks where good data isn't obvious? Seems tricky.
It's absolutely critical, especially in RL. Data quality, diversity, relevance heavily impact performance and efficiency. And for open-ended tasks, no reliable verifiers exist to easily flag bad data or hard problems.
Right, we covered that.
Existing filtering often uses those problematic LLM as a judge setups. So DRO introduces a generic and dynamic filtering mechanism leveraging R3 itself, enhances data efficiency without manual prompt engineering or external verifiers.
How does this filtering work?
It's quite smart, operating in 2 stages, happening regularly during training.
Stage 1.
Stage 1 filters out beyond knowledge or extremely difficult questions. The idea is RL training effectiveness depends on the model's existing knowledge. So for each question, DRO samples n cot traces, 16 or 32.
Okay.
Then for each trace, it evaluates self-certainty over the reference outcome tokens. But instead of raw log probs, it uses token rank as a proxy for difficulty. Higher rank means more unexpected, harder to predict.
A surprise ranking.
Kind of. It computes the average rank of the bottom percent, say 5–10%. Highest ranked tokens, the ones the model found most difficult.
Okay, average difficulty score.
Right. The logic. If none of the n-generator responses achieve a low enough average rank, meaning the model struggled even with easy parts of the reference, the question is deemed too hard or beyond its knowledge for now.
And it gets excluded.
Temporarily excluded from that training round. Prevents wasting compute on problems it can't learn from yet. Streamlines learning.
Smart. What's stage 2?
Stage 2 filters out questions with low reasoning variation. After removing the impossible ones, this tackles the opposite. Questions too simple or that don't elicit much varied reasoning. Not much for optimization to work with.
How does it identify those?
It cleverly uses the R3 scores. Specifically, it computes the maximum per token standard deviation max across the n-sampled COTI traces for that prompt.
Back to standard deviation reflecting reasoning impact.
Exactly. High max means high reasoning-induced variability. Prompts are ranked by max, and a proportion of the lowest-ranked samples, simple questions, little reasoning variation, are removed.
Focusing training on where reasoning matters most.
Precisely. Maximizes the impact of each training step.
And it's dynamic.
Yes, happens regularly, adapting as the model learns. Plus, 10% of data carries over from the previous set for continuity, creates a dynamic curriculum, progressively tackling harder challenges, robustly cuts training time, improves convergence, no human needed. A self-optimizing curriculum.
That sounds like a beautifully integrated system. Filtering adds sophisticated self-correction even to the data itself. This all sounds technically solid, but, the proof is in the performance. What data sets did they use, and how did DRO actually perform against these diverse challenges?
Absolutely. The experimental validation is where it gets really exciting. They evaluated DRO on 2 quite diverse data sets covering the spectrum from open-ended to structured reasoning.
Okay, what were they?
First, ParaRev, a benchmark for long-form paragraph revision. Over 48,000 original revised paragraph pairs from scientific papers with reviewer comments.
Real-world data.
Exactly. They focused on initial revisions, usually the most complex changes, and crucially included full paper context for proper reasoning. This really pushes open-ended understanding, rephrasing, restructuring, like making the LLM a sophisticated editor.
Challenging. What was the second data set?
Second, FinQA, focused on numerical reasoning over financial data. Over 8,000 samples. Context, questions, numerical answers.
More structured, like math problems.
Right. FinQA tests if R3, designed for open-ended ambiguity, can still hold its own, or even offer advantages where traditional verifiable answers exist, a great generalizability test.
And the models and setup?
Powerful, publicly available models. DeepSeek R1 distilled Quinn 7b and 14b. The setup was extensive. Learning rates, sampling, repetition penalties, GRPO specifics like scaled rewards for stability. They empirically found setting entropy regularization beta to 0.001 improves stability in interesting detail.
Sounds like a serious setup. What about compute?
Formidable. 3 nodes, each with 8 NVIDIA A100 GPUs, using standard tools like Hugging Face TRL, Deep Speed for distribution, VLLM for fast rollouts, and R3 computation. A robust, well-resourced experiment.
And evaluation metrics, how do they judge success?
For FinQA, straightforward numerical correctness, 2% tolerance, pretty standard for math tasks.
Okay, and for ParaRev, the subjective one?
For ParaRev, they use pairwise win rate. Powerful LLMs GPT-4o and Claude 3.7 Sonnet acted as impartial judges.
Using LLMs to judge LLMs, we talked about the issues there.
They were careful. Meticulously adapted the applicable prompt for the revision task, providing full context. Their validation showed this prompt design aligned very strongly with human preferences, suggesting reliable evaluation.
And using both GPT-4o and Claude helps.
Yes, critically. Using both helps mitigate potential self-enhancement bias from a single LLM judge. Adds confidence to the results.
That's a truly robust setup, and using multiple LLM judges for ParaRev is smart. So let's dive into the core results for ParaRev, the really challenging open-ended task. How did DRO with R3 stack up? Does it tackle open-ended reasoning effectively?
The ParaRev results are frankly incredibly compelling. They really underscore R3's power. First, regarding R3's superiority in reasoning quality and alignment. DRO R3 got significantly higher win rates against GPT-4o compared to all baselines.
How much higher?
It beat the base DeepSeek model by 8.0% judged by GPT-4o, and even more, 10.2% judged by Claude 3.7 Sonnet. Consistent, robust improvement.
It's all.
But here's the truly remarkable bit. DRO R3, a much smaller model, 7b or 14b, actually surpassed GPT-4o itself in win rate when GPT-4o was the judge.
Wait, the smaller model beat GPT-4o according to GPT-4o?
Exactly. Think about that. A smaller model, fine-tuned with this self-contained reasoning optimization, was preferred by a massive state-of-the-art model on this complex task. That's not incremental, it's huge.
Wow.
It shows R3 enables reasoning quality rivaling or even exceeding much larger general-purpose models for specific tasks. Plus, DRR3 outputs were closer in length to human references, more faithful, efficient edits, aligning with human preference.
Okay, impressive against the state-of-the-art. How did it compare to baselines using other reward types, like Rouge?
Comparing R3 against Rouge-based rewards, the difference was stark. R3 yielded win rates 16.0% higher, GPT Judge, and 20.7% higher, Claude Judge, over Rouge baseline.
Why such a big difference?
Because models trained with Rouge often just left the paragraph completely unchanged. Rouge favors textual overlap, right? So the model learned the easiest way to maximize Rouge was to just reproduce the original text.
Defeating the whole purpose of revision.
Completely. R3, focusing on reasoning consistency, avoided this pitfall entirely.
And R3 versus the naive aggregate certainty rewards, the one that suffers from token blindness.
Right. R3 consistently led to much higher win rates compared to aggregate certainty, regardless of length control, up to a staggering 4.25 times improvement over the DRO agar-R baseline.
4.25 times.
Yeah. Really underscores the importance of weighting those reasoning reflective tokens. It's critical. Interestingly, strict length control actually hurt performance for aggregate certainty, suggesting rigid length limits can suppress reasoning if the reward signal isn't focused correctly.
Fascinating. What about insights from the training process itself on Pararev? Did R3 change how the model behaved during training?
Yes, some fascinating training insights. First, significantly, R3 stimulates much longer, more elaborate reasoning. Figure 3a in the paper shows R3 encouraged cut-T sequences to grow steadily from 1,000 tokens to over 2,500 tokens.
Deeper reasoning.
Indicates much deeper, more explicit reasoning. In stark contrast, aggregate certainty models saw reasoning length collapse below 100 tokens.
Wow, it learned to skip reasoning.
Exactly. The misleading aggregate signal rewards shorter paths. R3 prevents that.
Any other training observations?
Yes, an interesting, unexpected, implicit improvement in textual similarity. Even though Rouge wasn't in the R3 reward, Figure 3b shows Rougel F1 scores improved substantially, Bait 1.4 to 0.7, early in R3 training.
So better reasoning led to better surface text alignment.
It suggests so. Optimizing those reasoning reflective tokens seems to naturally improve surface alignment as a positive side effect.
And the filtering. Did it help efficiency?
Yes, filtering efficiency was remarkable. Figure 3c shows the dynamic filtering reduced training time by 45% while achieving comparable final rewards and smoother convergence. Demonstrates its robustness and efficiency, faster, stable training.
That's incredibly impressive for an open-ended task like Pararev. R3 seems to capture the logic and intent. But what about FinQA, the structured math task? Can R3 hold its own there? Or does it lose its edge where verifiable rewards exist?
Crucial question for generalizability. On FinQA, the results show R3 achieves improvement comparable to rewards from an ideal verifier.
Ideal verifier, meaning the actual correct numerical answer.
Exactly. For FinQ, you can use a correctness-based reward, 1 if the number's right, within 2% tolerance, 0 otherwise. That's the gold standard here.
So how did R3 compare to that gold standard?
Strikingly well. DRO-R3, without needing that explicit correctness signal, got very close. Only 0.9% short on pass at 1, getting the single best answer right. But it actually outperformed the correctness baseline on pass at K for K02.
Better if you look at the top 2 or more answers.
Yes, meaning if you want a broader range of correct solutions, R3 was actually better. Powerful demonstration of versatility. It can work well even where ideal verifiers could be used, making it viable when they're hard or impossible to get.
Does it still beat the aggregate certainty reward on this shorter output task?
Yes, R3 clearly outperforms aggregate certainty even on FinQA. Even with short numerical answers, R3 showed significant superiority. Compared to the base model, DRO-R3 achieved 4.15 times higher improvement than DRO-AG.
So reasoning reflective tokens matter even for math, like a decimal point or sign.
Exactly. Confirms the concept isn't just for long text. Even a single decimal point, negative sign, or crucial digit could be a reasoning reflective token, signaling the correctness of complex numerical reasoning. R3 finds these microsignals.
What about the training insights for FinQA? Anything interesting there?
Very telling insights. First, steady R3 reward improvement and stabilization. Figures 4a and 4b show DRO consistently improved R3 reward while reducing its standard deviation. Stronger, more consistent reward attribution, more stable, reliable performance. Good learning signs.
Okay, anything else?
Second, again, a clear emergence of longer reasoning. Generation length steadily increased from 1,000 to over 3,000 tokens, like in Pararev. But here's where it gets particularly interesting, a bit of a puzzle.
A puzzle. How so?
While the R3 improvement started to slow down and saturate around training step 6, the reasoning length continued to grow almost linearly well beyond that point.
That divergence is captivating. The model keeps elaborating its reasoning even when the explicit R3 reward isn't improving as much?
Exactly.
So What does this all mean? Are they just being verbose, generating useless text, or is something deeper happening inside the LLM?
That divergence is fascinating and suggests something more profound than just verbosity. It implies that even after immediate R3 gains saturate, the model might be continuing to explore richer explanations, build more robust intermediate steps, or engage in extended self-reflection not fully captured by the current R3 function at that plateau.
So reasoning length could be a proxy for depth, even if not directly rewarded further.
It seems plausible. It's almost as if the model, given the freedom, keeps expanding its internal thought processes, maybe creating more comprehensive, even redundant explanations for robustness or consistency, or maybe making reasoning more transparent.
So it might have an intrinsic drive for understanding beyond the task score.
It's a very intriguing possibility. Are they building a more complete internal model? Or just exploring permutations? Huge area for future research what's happening in those longer traces. Do LLMs have a drive for completeness?
This deep dive into DRO and R3 paints a truly compelling picture of LLMs learning to refine their own thinking in this self-sufficient way. Connecting this to the bigger picture, what are the broader implications of a fully self-contained training setup like this for the future of AI?
The implications are potentially immense. By removing reliance on slow, expensive human annotators or complex, fallible external reward models, this self-contained setup drastically reshapes LLM training. It's a profound shift towards greater autonomy in AI development.
How so, practically?
It can significantly accelerate training for complex reasoning, fundamentally reduces costs for data annotation and reward model development, often the biggest bottlenecks, and crucially allows reasoning optimization to scale unimaginably.
So more autonomous AI development.
Exactly. Points towards a future of more autonomous AI refinement, where LLMs continuously improve their own reasoning without constant human oversight or expensive external feedback loops. A critical step towards truly self-improving, self-correcting AI. Could democratize advanced LLM capabilities by lowering the tuning barrier.
That's a truly revolutionary prospect, AI learning to teach itself. But okay, the paper shows R3 works across long-form and structured tasks, great generalizability. Are there technical limits? What reasoning tasks might still challenge this approach?
Excellent question. No silver bullet. R3 fundamentally relies on identifying those reasoning reflective tokens via likelihood variations across Kati traces. Works great when there's a reasonably clear mapping from reasoning to output tokens.
But what about more abstract tasks?
Exactly. In highly abstract or truly novel reasoning, maybe creative tasks with no clear reference, or novel problem-solving domains where no correct output exists beforehand, identifying those tokens might get much harder.
The signal might be too diffuse.
Could be. The self-certainty signal might be too diffuse, variations too subtle. Think generating a new scientific hypothesis or abstract art. The reasoning output link might be too indirect for R3 to pinpoint key tokens effectively. Further innovation needed there. It's a fantastic leap, but reasoning frontiers are vast.
And back to that fascinating observation. Reasoning length growing even after R3 reward, saturated in FinQA. What might this imply for our understanding of LLM intelligence or internal thought processes beyond just task performance?
That divergence is truly one of the most thought-provoking insights. It suggests LLMs aren't just simple reward optimizers. Even after R3 gains slowed, the model kept expanding its reasoning.
So what could it be doing?
Several possibilities. Maybe exploring a broader reasoning space, generating more robust, redundant, or generalizable explanations than strictly needed for the reward, building more comprehensive internal representations, developing a deeper understanding not fully captured by the current reward.
Like generating multiple ways to verify a math answer.
Possibly. Or providing alternative solution paths. It highlights that LLMs might have an internal drive for understanding or completeness beyond simple task scores. Poses profound questions. What other signals can we extract from these longer traces? How can we reward this deeper exploration?
Powerful, almost philosophical thoughts. To wrap up, what's the next big technical hurdle in optimizing LLM reasoning, given DRO and R3? What crucial problems does this paper not explicitly solve? What's next for the research community?
I think one big hurdle is discerning truly causal reasoning versus mere correlation in open-ended text. R3 captures consistency brilliantly via likelihoods, but moving towards models performing robust causal inference explaining why something causes an outcome, not just correlating it, is a significant frontier.
Especially for things like financial advice.
Exactly. Can it explain why a strategy causes an outcome, not just that it worked before?
What else?
Maintaining reasoning consistency over extremely long contexts remains a challenge. Multi-document analysis, long projects. Current context windows and compute costs are limiting. Scaling that efficiently is tough.
And reasoning with dynamic information.
Right. Integrating real-time, dynamic info for reasoning, especially for agile decision-making in evolving environments. That's beyond static text fine-tuning. How can LLMs reason with constantly updating data or perceive and reason about the world in real time? Key future research areas.
So what does this all mean for you, our listeners? Today, we've taken a truly fascinating deep dive into direct reasoning optimization and the innovative reasoning reflection reward. We've seen how LLMs are learning to become their own best teachers for complex, subjective, open-ended tasks. It's a breakthrough promising to reshape AI training and deployment.
Yeah, the core innovation is the model's remarkable ability to autonomously identify and leverage those reasoning reflective tokens from its own internal self-certainty. This drives significant performance gains, substantial cost reduction on tough tasks like paragraph revision and financial QA, paving the way for more autonomous, capable AI.
And as a final provocative thought for you to mull over,
Consider this. If LLMs can autonomously identify and reward the critical moments in their own internal reasoning, continuously improving their thinking without constant external human oversight, what new frontiers of self-improvement, self-discovery, and maybe even general intelligence become possible in AI? It's a future being built, one reflection at a time.